In this video, we'll look at exponential growth and decay functions. An exponential function is given by f of x equals b to the x, where x is any real number, b is positive, and b is not equal to 1. You'll have exponential decay if b is between 0 and 1, not inclusive. So b is greater than 0, but less than 1. Then you'll have exponential decay, and your graph will look like it's falling down towards that horizontal asymptote. You'll have exponential growth if b is greater than 1. So in that case, your graph will start at some initial low point and shoot up to the right in an exponential way. So we'll look at examples of both. We're going to start with exponential growth. Exponential growth occurs when the base is greater than 1. So when b is greater than 1. The formula for exponential growth is f of x equals a, some initial amount, times 1 plus r raised to the x power. So 1 plus r is in parentheses, and that whole quantity is raised to the x power. A is the initial amount, r is the growth rate, and x is the number of time intervals. So here's an example. A city has a population of 350,000 people. Suppose that each year the population grows by 6.25%. What will the population be after 6 years? Round your answer to the nearest whole number. So the first thing I want to do is grab that growth rate. And I want to write the rate as a decimal. So if you recall, to get a percentage written as a decimal, you're going to divide by 100, which would essentially move the decimal point 2 spots to the left. So 6.25% would be 0.0625. So I moved the decimal 2 spots to the left to get my percentage written as a decimal. Now my initial amount is 350,000 people. That's going to be my A, my initial amount. And then the time interval is years, and we're talking about 6 years. So this is telling me that X is going to be 6. So the population after 6 years, I would write that as P of 6, is going to be the initial amount, so $350,000. I'm sorry, it's not dollars, it's people. So 350,000 people times parentheses 1 plus 0.0625 raised to the 6th power. And I just have to put that into a calculator and I've got my answer. So I'll put in my 350,000 people, parentheses, 1 plus 0.0625, close the parentheses, raise that to an exponent of 6, and we've got our answer. So we've got 503,549. It says round to the nearest whole number, and the digit after the decimal is a 9. So I would round that 8 up to a 9. So 503,548. 503,548. 4, and it was actually 9 because that 8 rounded up. So people. 503,549 people. So remember this when you're doing exponential growth. A is the initial amount, R is the growth rate, X is the number of time intervals, and your exponential growth is A times quantity 1 minus R quantity to the X. Now let's look at exponential decay. That occurs when the base is less than 1. But remember, the base has to be positive. So that's when B is between 0 and 1. Exponential decay is used in carbon dating to tell how old fossils are and in telling when it will be safe to be in a location where a radioactive event occurred. There are other applications as well, but those are a couple interesting ones. The formula for exponential decay is f of x equals a times parentheses 1 minus r, close the parentheses, to the x power. So the only way it differs from the exponential growth is you're subtracting the rate from 1 instead of adding the rate to 1. Let's look at some examples. So the first example says that a certain forest covers an area of 2,500 square kilometers. Suppose that each year this area decreases. That's what tells us that we're dealing with decay. So that word decreases tells us that we're going to have decay by 7.25%. What will the area be after 11 years? So our time intervals are years. So 11 years is going to be 11 time intervals. So we'll have x equals 11. Our initial amount was 2,500 square kilometers. So that's our initial amount A. And our rate is 7.25%, which would translate to an R of 0.0725. Round your answer to the nearest square kilometer. So the size, we're going to have, we'll call it area. So I'll say A of 11 is going to be 2,500. That's our lowercase a value. Parentheses 1 minus 0.0725 raised to the 11th power. And so we just have to plug that in. So we'll have 2,500 parentheses 1 minus 0.0725, close the parentheses, do an exponent of 11, and we've got our square kilometers. It says round to the nearest whole square kilometer. So because the digit after the decimal point is a 4, I would leave the 2 as it is. So I would have 1,092. So I get 1,092 square kilometers. All right, let's look at one more example. The half-life of a radioactive isotope is the time that it takes for the quantity of the isotope to be reduced to half its initial mass. Starting with 210 grams of a radioactive isotope. So let me identify that. 210 grams tells me that my initial amount is 210. How much will be left after 5 half-lives? Round your answer to the nearest gram. So in other words, we're cutting this in half 5 times. So basically, I'm going to have 210 times, I want to cut it in half 5 times. So I'm going to multiply by 1/2 to the 5th power. That would be the same as dividing by 2 5 times. So I'll go ahead and do that in the calculator. So I'll have 210 times, and then I'm going to do parentheses. You can either do 1/2 or 0.5. I'll do 0.5 to the power of 5. And it says round your answer to the nearest gram. So I'm going to have 7 grams. So this was a little bit different than the previous ones. Although you could think of it as a rate of 50%. And so if you wanted to set it up using this, so f of x equals a times 1 minus r to the x, you could think of the rate as being 50%. So your r would be 0.5 or 0.50. And so you would end up with 210, 1 minus 0.50 to the x, but that just comes out as 210 times 0.50 to the x, which is what we used here. We basically said 210 times 1/2, and then 5 half-lives we did to the 5th power. So remember those formulas for radioactive growth, for exponential growth and exponential decay. Those formulas, a times 1 minus r to the x, and a times 1 plus r to the x are not on your formula sheet, but you do need to know them.